Let me ask you a question. Imagine a scenario where a person applies a force of about 400 newtons to push a car, but the car does not move. What do you think the work done by the person in pushing the car would be? Congratulations if your answer was 0. It's correct. But do you know why, in spite of applying 400 newtons force, the work done was 0? Welcome, class. Today's topic is work, power, and energy. In simple terms, work is said to be done if it causes the object to move. Now, the movement can be either in the direction of the force applied or in the opposite direction. If force applied causes the object to move in the same direction as that of the force, then the work done is said to be positive, as illustrated in this video where a boy pushes a box and it moves in the same direction. In this example, there are two types of work being performed. First, there is positive work when the boy exerts a force to push the ball upward. Second, as the ball rises, it performs negative work with respect to gravitational force because the upward movement of the ball opposes the downward pull of gravity. In the last case, let's examine an example where a porter is carrying a suitcase and walking towards us. The porter exerts an upward normal force, but the suitcase moves in a direction that is perpendicular to the force applied. This is another classic instance where we say the work done is 0, even though the porter is clearly doing the work of transporting the suitcase to its destination. Mathematically, work done is defined as force applied multiplied by the displacement achieved multiplied by cosine theta, where theta is the angle between the force applied and the direction of movement. In the previous scenarios, we assumed that the force acting on the object is constant. However, in reality, this is often not the case, as the force frequently varies over time. In such situations, to determine the total work done, we calculate the integral between the initial and final distances. Essentially, the area under the curve represents the total work done when the force changes. Kinetic energy is the energy an object has because of its motion. The faster something moves and the heavier it is, the more kinetic energy it has. Imagine you're riding a bicycle. When the bicycle is stationary, it has 0 kinetic energy. As you start pedaling, the bicycle gains speed. It gains kinetic energy. The faster you go, the more kinetic energy the bicycle has. Potential energy is the stored energy that an object possesses due to its position or condition. It's like energy that's ready to be utilized but isn't actively doing anything at the moment. Mathematically, potential energy can be calculated using the formula mass times gravitational acceleration times height from the ground. Now consider a small pebble resting on top of a large rock. Which do you think has more potential energy? And why? Can you provide an answer? The force exerted by a spring is described by Hooke's law, which states that F equals minus kx. In this equation, k represents the spring constant, while x indicates the amount the spring is stretched or compressed from its equilibrium position. Let's consider different conditions. 1. Positive force. When the spring is stretched by the hand, it exerts an outward force, resulting in a positive force, which overcomes the spring force. But the spring has natural tendency to restore its original position, which is opposite to the external force. So spring force does a negative work of k x squared by 2. Scenario 2, negative force. When the spring is compressed by the hand, it exerts an inward push, resulting in a negative force. But the spring has natural tendency to restore its original position, which is opposite to the external force. So spring force does a negative work of equals k x squared by 2. Scenario 3, equilibrium, zero force. If the spring is at its natural, unstretched and uncompressed length, then it is said to be in equilibrium, meaning the force exerted is zero. Imagine a roller coaster at the top of its track. At this height, it possesses a lot of potential energy. As the roller coaster begins to descend, this potential energy transforms into kinetic energy, which is the energy of motion. When the roller coaster reaches the lowest point of the track, almost all of its energy is kinetic, meaning it is moving at its fastest. As it climbs the next hill, the kinetic energy is converted back into potential energy. This continuous back and forth conversion of energy occurs throughout the ride. The fascinating part is that in the absence of friction or air resistance, the total mechanical energy, the sum of kinetic and potential energy, remains constant. This principle is known as the law of conservation of energy. Power is defined as the rate at which work is performed. When two people lift the same weight to the same height, they perform the same amount of work. However, if one person does it faster, they have more power. Power is measured in watts. 1 watt is equivalent to 1 joule of work done per second. Thanks for your time today. Let's meet in the next class. Until then, goodbye.